Hello,
Hello, how are you?
I am fine.
All right.
I'm kind of working on my proposal for GSOC
Oh, good.
for the community sustainability, open source community sustainability project.
Yeah.
But yeah, apart from that, all well. How about you?
Oh, pretty good. Yeah, good luck with your proposal. So you're not having any problems with it?
Not exactly. I'm almost done. I was just refining it, and I was thinking of sending over a first draft for you to review. I just wanted to confirm some things.
Yeah.
I'm following the format suggested by INCF.
Okay.
I hope that'll be fine. And for the timeline, like the proposed limit, I'm suggesting a 12-week timeline.
Yes.
With like bi-weekly milestones. So, is there anything you would advise, or does that seem fine?
Yeah, that's fine. And I've been telling people that, you want to work your timeline out so that it has, like, you know that you can do something, but if something fails or falls behind, you can switch to something else for a while. And then, have like a couple weeks at the end where you're kind of finishing things up. So, the idea would be that you want to have things define what you're doing week by week, but you also want to be flexible. We may have to rescope it into the project, so far into the project, but that's okay. That's what you're supposed to learn in the program, is how to manage your time on a project like that. But, you want to start off with, 12 weeks of work, basically. How much work would be a 12-week chunk? And, you don't want to propose like 2 years of work. You don't want to propose 2 weeks of work. You want to propose 12 weeks. So it's it's challenging, but that's and then we can always, like I said, we can always rescope it later, but that's not preferred because then we have to kind of do things improvisationally, and
Right, right. I have tried to do the same. I'll send you a draft in some time,
Okay.
and maybe you can just review it before I submit it on the official website. Should I be sending it to both of you?
Yeah, you could get Jesse's feedback if you'd like. I mean, I'm usually giving. It's just a very minor feedback to look at it and see if it looks like something that was,
Right.
acceptable, right?
Right. Sure. Thank you.
You're welcome. So, any other questions or comments?
None from my side. Just like one other thing about my proposal was like I noticed in the previous models that were built, there was like there was some focus on the visualization. Like most of them were using NetLogo,
Right.
and the simulations could be visualized. I have a feeling it will be slightly difficult in the kind of framework that I've proposed for integrating LLMs directly into that. So I mean, I have proposed it as an optional milestone for now. Considering that the other deliverables are done, I will try to work on the visualization. It is possible. One of the frameworks has done it, but the code needs to be like completely created in a Python kind of visualization. I don't think I'll be able to integrate with any framework like NetLogo as of now. So is that like okay? Like for the main part of visualizing mine, I've kind of proposed graphs which can visualize the metrics changing throughout the simulation within the agents or the environment's metrics. So is that fine, or is the visualization something that I should have a heavy focus on?
Well, we haven't done anything with visualizations yet in the project, so that might be something to highlight. And I don't know how you want to implement it. So we've used NetLogo, like kind of as our original platform that we had, and we've published things on the web using NetLogo. But there's also, of course, Mesa, which is the package through Python, which allows you to do agent-based modeling in Python. I think we also explored Pygame, which is another Python package. And those are, I don't know if those would give you visualizations necessarily as good as NetLogo. But, you know, like you might say in the proposal that you would, you know, kind of, there's this couple week period at the beginning, the community period, where you have to sort of figure out exactly what you're going to do. So you might say, I'm going to look into NetLogo versus NISA or Pygame and see how their visualization is for this thing that I want to do. So you want to visualize some of the metrics and how they're changing. That would be good, but we want to know what the best platform is. And I don't know if you have an idea of that, but there might be, you know, a good way to do that. You might try a couple alternatives and see which one is best. But you don't have to say right now what that is. You can try a couple of alternatives and see which one works best.
All right, sure. Thank you.
You're welcome. So it looks like Amanda's here. Hello, Amanda.
Good morning. How are you
Good
guys?
morning. All right. Looks like Jesse gave an update. Getting ready for GSOC. Also, good news for plot twisters about being accepted to an inclusive gaming conference. And some more Joe Pro movement. Okay, that's great. Yeah, I know. It's always good to have like different projects moving along, and you know, sometimes you have to wait for good news and that sort of thing. So, Amanda, do you have any updates or?
So we didn't meet for Cognition Futures this week, I believe. I know I couldn't make it. But the cybernetics reading group met, and that went well. We are working through a paper, I forget the full name, Naturalizing Relevance Realization. Basically, the gist is that what organisms do when they extract meaning from the world is like fundamentally not computational. But it's an interesting argument for that. So I believe we will probably finish two weeks from now. I guess I might be open to meeting next week. It's hard, the every other week is nice in some ways, but then when we're working through it, like one particular paper, sometimes that feels like a long gap. But yeah, but that's going well. I created a Notion page for a kind of like mission statement for that group. I don't feel like there's any rush to fill that out because we'll like develop our thoughts as we continue with the group. But I can try to find that and share it in the Slack, and maybe we can add some notes. One thing that came up a couple weeks ago that I do want to continue with is maybe using like memory as a case study, in a sense. I think that the short version of that is like, what would a properly 4E account of memory be? And how can cybernetics maybe help us with that? Basically the storage kind of metaphor for memory. It's like, well, it's so pervasive that it almost doesn't seem like a metaphor. Like, of course we store memories. But I think there are some issues with how that's talked about often. Right. I think that's going to be a focus of the group. Otherwise, I don't think I have any updates.
Okay, well that's great. Yeah, thanks. Yeah, that's always the problem with having 2-week intervals in meetings. In fact, 1-week interval in meetings sometimes is you're working on something and you're kind of going from meeting to meeting and you kind of forget everything. You know, you lose the sort of the mental frame of what you're doing.
Right. I think it worked well when we were working on like one book, and we could do a chapter every other week, but it is harder with papers.
Yeah.
But that being said, I do like focusing on papers. Maybe we more intentionally pick shorter ones that we can definitely get through in an hour, or we just commit to maybe not completely getting through every paper, because I do think it's valuable even if we just like kind of get the gist and decide what we like about it and what we don't, and then move on.
Yeah, I think that's actually a good idea because, like, I think, analyzing the entire paper is not always necessary, but I think
Yeah,
like
it's
some
been
of the
picking good
paper,
papers.
what was it?
I don't think we've spent too much time on any of these papers, but maybe, moving forward, we commit to just doing one per meeting.
Yeah. Yeah, I mean, it's the papers are pretty dense. I mean, so that's that's another problem. Like, there's so much there you can get out of them, and getting the gist is fine, but sometimes you want to get the details, and it's important for other things. So yeah, it's good. Yeah, let's think about that mission statement for the group. Yeah, it's always good to have like a good mission statement. You know, when we started that project, it was kind of like, revisiting cybernetics as kind of informal, what the goals were. So, no pun intended. But having a place fitting that project into the world is good. To have a more specific aim in mind there.
And I think we have talked a bit about like what the aims are. It'd just be nice to write them down in one place.
Yeah, so that's great. So this week, yeah, we didn't have a DivaWare meeting. We had no cognition futures meeting. We had a cybernetics meeting, and we haven't started our open source meetings yet. But I've been meeting with people about their projects, and so the project proposals for GSOC are due on April 2nd, which is Tuesday. It's sort of like that. I can't remember. We put it in the Slack. The time, it's April 2nd at like 1800 hours UTC, which is, depending on where you are in the world, could be April 1st here. It could be, so just make sure that you know that it's April 2nd, but it's that UTC time. So wherever you are in the world, it's going to be maybe a little bit different, maybe a little bit off for you. No, I would just get it in the first on Monday early, and then forget about. You don't have to worry about pushing the boundaries. And you have to have a proposal in. So word on proposals. People are off every year. We get more proposals than we can fund, unfortunately. But that's the way this works. So the way they usually do it through INCF, we're sponsored by INCF. They get a certain number of slots from GSOC, then we get a certain number of slots from INCF. And depending, we have to rank them, and we have to say, this is how many people we want, and then they give us that or not. Sometimes, some years it's been as little as one person. Some years we've gotten everyone we've wanted. So it's, it's a real gamble in that sense. If you can definitely apply to more than one organization at a time, that's acceptable, but you can only take one position at a time. And then you have to once you get your proposal in, you just wait until May. I think it's May 2nd when you find out, so it's a whole month. So, and then if you don't get selected through the program, you can still participate in the summer. Over the summer, we're going to have a meeting, which is an open source meeting, where every week we're going to have people are going to give updates on their progress. We're going to have special topics that we cover, and I think it'll be a great use for people. And hopefully, if you get selected, but if you don't, you can still work with us over the summer. If that's something you want to pursue, and maybe turn it into something that you can get funded later. Maybe next year's GSOC or some other project. We've done this before where we've had people who have applied for grants through the university, where they've done another round of GSOC and got the project funded. So it's worthwhile. So, but it's up to you. So I don't want to give anyone any false hope, but I also don't want to say that, you're kind of doing, it's a waste of time. So, looks like Himanshu's here. Hello. We have some things in the chat here. Yeah. Oh yeah, Amanda posted on the Cybernetics reading group. She made some notes in Notion, so that's the mission statement. And yeah, we can talk about that as we go along. How we want to have that, where we want to fit into. I imagine there'll be multiple aims in terms of how that, how we can use cybernetics, or we can understand cybernetics, or whatever. And then of course we're working on that paper. So that paper, I think, will be one sort of way to put that out in the world. The 4E aspect is another way where we have this, things that probably people haven't really thought about before, but are maybe relevant to what's going on in the world, what people are interested in reading about, and so forth. I think Sarrah gave an update. She had some questions about GSOC. Shubham or Himanshu, did you have any updates or comments? Right. So Himanshu says, I like the approach Sarrah is taking with large language models and would be happy to know more. So this is Sarrah's. She gave a presentation a couple weeks ago on large language models and agent-based models and things like that. So that is very interesting. I don't know if she has a lot more to say about it right now. Definitely the proposal, we'll be reading the proposals. And yeah, I don't know if you have any more to say about it, Sarrah.
Not really. I could, if Himanshu would like, I could share, the same way I'm sharing it with you and Jesse. I could share a copy of the draft of the proposal and the approach I've planned so far.
Yeah, I think so. That would be good.
Yes.
And then Jesse asked, are there any other updates on the Royal Society Saffron paper? Well, not really. I heard from Adam Saffron, and he said it's a great paper. So, or it looks like it could be a great paper. We don't know yet. We just put the abstract in. So that's good. There's a positive response from the editor, and so yeah. Other than that, I don't think they've moved on it too much more. I mean, at some point it's going to be due, and I think it's about June 1st. They might move the deadline around we usually do. But we'll just have to keep that in mind as we move along. And I've been kind of spearheading this, so I need to go back and kind of tighten things up, and then we'll probably review it closer to the deadline, where we'll go through and we'll kind of do a line by line read or a section by section read and see where we are with it. Because we've met a couple times on this, and I think we're getting there. I think the basic premise is pretty solid, but the parts maybe need to be thought through a little bit more. But that's fine. That's usually what happens. So one piece of news is that this is a paper that myself and Daniela Cialfi and Avery Lim and Jesse have worked on. We've been working on this idea of Gibsonian information. And so we did a conference paper on Gibsonian information a couple years ago now, and that was a very short paper. It basically introduced the idea. It's basically the idea of using ecological psychology as a means to characterize information in the nervous system and in the environment in that interaction. And so this is a longer version of this, where it's not the conference paper where it's very short and has a simple description, but it's much longer and has a lot of description of like some of the mathematics and some of the examples, and some, especially the ties to ecological psychology. So this paper actually has some very explicit links to the ecological psychology literature and the things we're talking about. So, for example, we talked in the Cognition Futures group meeting about the Raja paper from 2018, which is where, it kind of lays out some of these ideas about ecological resonance. There's some other things in the literature that needed, I think, to be addressed more directly. The conference paper didn't really have that. So this is that paper. It's a fairly long paper. It's 48 pages. So it has like a lot of it. And it's called a primer because, you can go through and hopefully apply it to your work, although I don't really know if it's, I don't know how applicable it is. It certainly doesn't have any software associated with it because it is a theoretical paper. And so, at some point, I'd like to be able to create software that would model some of these processes, but we're not quite there yet. It does talk in terms of like maybe agent-based modeling or internal modeling. So those things are kind of there, but they're not quite sort of codable, I guess. So this is the paper. The idea is that you have sensory information and it forms these patterns in the environment, and there's a flow of sensory information. It comes into the agent. The agent can move around the environment, that can turn their orientation, and there are all these flows of information. But the key here is that it's Poisson distributed, meaning that sensory information isn't like this gray fog. It has structure in it. It has clusters of things. Sometimes they're actual objects with a label. Sometimes they're not. They're just kind of like, bursts of light or, bursts of wind or whatever. And so those things kind of come in at that rate. They come in over time. So you can use a Poisson process to model that process of sensory information coming in. And then once the sensory information is sort of transduced, let me see if I can find this one. Okay. Then it's that information is encoded in an internal communication channel. And then there's a decoding for behavior. So that's what we have here. We have this communication channel externally, which has a spatiotemporal dependence. There's this internal communication channel and then decoding. And so, there's not a lot of neural mechanism here, but the idea is that you can put in like a model, a neural model. You can put in like a conceptual model. You can even put in one of our metabrain models and it would work. The idea would be that you have this channel here. You think of it in terms of like what we think about this in cybernetics, where we have an input, some regulation inside the model, and then output. And so there are a lot of concepts here that have been worked out. A lot of things having to do with collective behavior, observing collective behavior, producing collective behavior, this flow rate, which is this flow of information through the nervous system. There's decay, which of course, if you sometimes you lose information or you lose capacity, and so there's a decay rate. And then we can model the internal model as a sensorium, which is actually a term which I don't cite McLuhan in here, but it's a term from Marshall McLuhan on like the effects of media on the nervous system. In this case, it's just a combination of things that we're taking in. We're taking in different dimensions of sensory information in space and time, but we also have things like coherent movement, which is where you have these clusters of things in the environment, and they're moving in a sort of a coherent manner. So, you think about things like if you're observing a flock of birds, or if you're observing like a pattern in a chemical stew, those things can be sensed and they have a pattern to them. It's not just random. So there are a lot of things here that, we can do. We can put these together into a model of sort of the external model and then the internal model. And that leads to this sort of naturalistic behavior. This is a model of where we have this sort of connectome, where we have, it's sort of based on a Bratenberg vehicle, but it basically is an embodied version of this internal model. So you have sensory inputs here, you have effector outputs here, and then an internal processing here, interneuronal processing unit here. So, this is just breaking this down into a model where we can look at these Gibsonian information in these different compartments within an embodied agent. There are a lot of goodies in here. There are different examples of application domains, different submodels like this multi-sensory model where you look at different sensory streams and how they're aligned with each other. And, you can describe multi-sensory interactions with this language where you have these units, which are each sensory stream. You have a direction of movement or of sensory input, and then that leads to aligning the sensory output. So if each of these sensory streams have to kind of be aligned to have a coherent sensory experience. If they're not, then there's some correction that needs to be made, or there's some misalignment. And it's kind of hard to describe because we don't fully understand how sensory integration works. I mean, we have some good models, but something where, especially in a naturalistic context, it is kind of hard to understand how these things are put together. But if you have this sort of model where you have each sensory stream considered separately and then look at how they're oriented, sort of like an ensemble approach, then that makes it a little bit easier to understand, given a specific example like this rabbit hopping around in the grass, and there's this direct perception happening, and then there's this inferred perception, and we can look at it using a model like this. So yeah, it's and then there, we have links to dynamical systems. So there's this phase space diagram where, we look at different regimes of Gibsonian information versus delay. So GI is Gibsonian information, delay is here, which is like where things are delayed. So over time, you might delay certain information. It might get delayed through different processes, different noise in the environment. And so then you see that, like, when you have, higher levels of decay, you have collapse or high turnover. And so sustainability is in the middle where, you can have like a long-term interaction with the environment, long-term cognition. And so these are all just theoretical concepts at this point, so it isn't necessarily easily codable. Some of it is probably easily codable. Certainly we made mathematical representations there. But, it's a ways to go between mathematical representation and coding. Himanshu asks, can the concepts of this project be applied to Bradenburg vehicles as well? Yeah, that's sort of the intent, is to, enable this in embodied agents. So, the RIE model that I showed is explicitly made kind of for a Bradenburg-like model, where you have sensory input, you have sensors, effectors, and then these interneurons. So that's definitely something that can be done and understood in that way. So I wanted to highlight that. Oh yeah. Yeah, good. I wanted to highlight that. It finally made it out in the archive. It was something that we were reviewing internally, but I think it's, safe to say that, it's preprintable at this point. And then, we might find a home for it in a peer-reviewed journal. But, we might work out some of the details independently of that as well. So, okay. So it looks like Morgan's here. Hello, Morgan. Jesse says, thank you for doing all the heavy lifting on that. Yeah, this is something that we've been working on for a while. We've had conversations about it, and we kind of had the conference paper, so I decided we should have like a primer, a more detailed primer as well. Because we did have a longer preprint at one time, and it was on a different preprint server, but like the conference paper that was published was kind of like an abbreviated version of that, because we couldn't get, like, the word count was limited. So that got cut, and then that got moved over to another thing, and then that got worked out into this. So, yeah. We have a collaborator, Sarrah, and he makes an infrequent appearance in our Slack. And he, sometimes he makes some pretty good comments, or he gives some pretty good pointers to papers and things like that. So I'm always glad to see him show up in the Slack and make some comments or contribute there. So this is a paper, though, he put in the Slack this week. And this is from Science Advances. This is from 2019. So a little background on Sarrah. I think he's from Georgia, the nation of Georgia. And they have a really interesting language that's unique in a number of ways. And so he's mentioned this before, where, you have these, you have a language that's really interesting to study. And so we've talked about that before. This is another sort of linguistics-based paper. And this is something that kind of came up, I guess, in 2019, but it's really interesting because it has information theory in it. It has this linguistic aspect, this cognitive science aspect. And it's probably, there's some link to LLMs here. I'm not really sure if they bring up large language models, but I think it's relevant to that. So it's very good find by Sarrah. Thank you. And so this is, the title of this paper is Different Languages, Similar Encoding Efficiency. Comparable Information Rates Across the Human Communicative Niche. So this is where they analyze a bunch of languages, and they look at the sort of the information rate, or what they call the encoding efficiency of the language. So, if you're familiar with LLMs, there's this aspect where they learn language, they spit out answers. And part of this is sort of their language models that exist that are not large. We have like Bag of Words, for example, which is where we take words and we chop them up into pieces, into small, shorter stretches of letters. We put them in a pot and we draw from that. And we can build words. It's kind of like Scrabble, but for segments of words. And, there's this information theoretic aspect of that. Like, how many bits are transmitted? How many bits does it take to transmit an idea? How many words does it take to transmit an idea, and so forth? So we use Bag of Words. We can produce like, how many draws do we need to make to build like a word, or build to convey an idea? And language is kind of interesting because it's very fluid in that way. Like we can create, acronyms. We can create portmanteaus, which are combinations of words, and they have their own meaning. So the words that you learn have a meaning, and you've learned them. But you can create words and ascribe it a meaning, and as long as people find it interesting, they might start using it too, and then it becomes part of the language, and you get this new word. So this is oftentimes, in the United States, people do this a lot more than, on average, I think a lot more than other countries, because the United States are always trying to sell things, and so it's a melting pot of different cultures, or where people are speaking English. A lot of people speak English who maybe their grandparents or parents didn't speak English, and so it's not like England, where they have this very formal version of English. It's kind of more, it has to be kind of more constructed. But anyways, I don't want to get into that. But the point being is that language and words, in some languages where you have grammatical structure and semantics, there's this information encoding efficiency. So let's read the abstract here. I'm not familiar with any of the authors, so I can't say anything about that. But the abstract reads, language is universal, but it has few indisputably universal characteristics, with cross-linguistic variation being the norm. For example, languages differ greatly in the number of syllables they allow. So, they're different. Of course, English has a certain rule structure. Georgian has a certain rule structure. German has a certain rule structure. Bengali has a certain rule structure, and so forth. We can go across languages, and we can see that they're different. There's a lot of variation there. So, resulting in large variation in the Shannon information per syllable. So, I was just talking about Gibsonian information. One of the things you do in that paper is kind of draw a distinction from Shannon information, which is, of course, the thing that a lot of people are familiar with. And Shannon information characterizes sort of the variation in something. So, if you have, if you have a series of coin flips and it's heads, tails, heads, tails, heads, tails, that's the maximum amount of Shannon information. Because at every flip, you can't necessarily predict the next flip. It's not, if you have heads and the flip results in tails, if you had predicted heads because the last flip was heads, then there'd be no, and that happened, there'd be no information there because you know exactly what happened. But if the sort of the probability of a coin flip is that you can get to heads or tails, both with a 50% chance of doing so, then that's maximum information. You don't know what the next state's going to be, and so there's maximal information there by the next flip giving you that information. So that's basically the idea behind this. And so your syllables are going to exhibit Shannon information, but depending on the language you're speaking, it's going to vary quite a bit. Nevertheless, all natural languages allow their speakers to efficiently encode and transmit information. So every language, every natural language, allows speakers to efficiently encode and transmit information. And they talk about universality, which means that this is found across languages, although in this paper they only test languages from Asia and Europe. So, there are a lot of African languages, there are a lot of Native American languages that maybe are different, but, there are also like things like pidgin languages or, hybrid languages or dialects that might also be different. But in any case, these cross-linguistic or cross-cultural comparisons are useful because they give us some indication of like if you have a different sort of trajectory of evolution of that language, does it sort of result in the same set of properties, or is it just something that's, sort of beanbag that you can't that's not a property that's valued across languages. Okay, so we show here using quantitative methods on a large cross-linguistic corpus of 17 languages that the coupling between language level, which they define as information per syllable. So if you have a syllable, like, and this is kind of closer to our bag of words definition than, a single unit in a bag of words is like more or less a syllable. And then that has a certain amount of information. So this is the language level, and then at the speaker level, which is what they define as speech rate, or the speed of talking. So right now I'm talking, I guess, at a normal speed, maybe a little fast. If you want to have people understand you a bit better, you might talk more slowly. So that's, just because people can hear each syllable. So there's a link between speaker level and language level, but the language level is encoded sort of in the language as learned, and then the speech rate is something that the speaker can modify the way they need to. And some languages, people speak faster or slower. Like in some versions of Spanish, people speak really fast. Like the Cubans or Puerto Ricans speak a lot faster than like Spaniards. And it's harder to understand sometimes unless you've been exposed to that speech rate. So there are differences in kind of the way that's culturally defined, but also, just contextually. But anyways, if we look at the coupling between these two things, this results in languages encoding similar information rates, which they define as around 39 bits per second, despite wide differences in each property individually. So they say that languages are more similar in information rates than in Shannon information or speech rate. So that's kind of their insight here. So they talk about the information rate, which is the thing that is like bits per second, rather than looking at the raw Shannon information, which is just the number of bits per syllable, I guess. So the Shannon information here is the static number of bits per second. And then there's this information rate, or no, the information per syllable is Shannon information, and then information rates are the bits per second. Okay. And then the speech rate also is the speaker level or the rate of speech. So you're basically, you have time, you have just the static measure, and then you have something in between, but that's not really as predictive as an information rate. Languages are more similar in information rates and Shannon information or speech rate. These findings highlight the intimate feedback loops between language's structural properties on the one hand, and their speakers' neurocognition and biology under communicative pressures on the other hand. So this is where we have the language, and it has these structural properties. If you want to think of languages as offloaded information about the world, you can do that. Languages are often sort of shared cultural information. You pass down a language. Small children have to learn the language. Speakers can learn it as a second language. And we know from studies that language development has a number of neural correlates, but it's also something that we can do, at different rates of success. So, second language speakers often struggle a little bit more with learning the language. There's this immersion aspect where you have to be immersed in the language and so forth. So, there's this interaction between the neurocognitive milieu, as you might say, and the language is a structural thing. Having this system of, of rules and of words and of meanings that then interact with that. Thus, language is the product of multi-scale communicative niche construction processes at the intersection of biology, environment, and culture. So they're actually using this last sentence, they're kind of using another method here, which is niche construction. And I don't know how formal they get in terms of modeling that, but that's, if you want to read the paper, I can't remember what channel Sarrah put it in, but I can share it with you as well in the Slack. So yeah, this kind of talks about actually, so they take the view that language is universally used and can have universal characteristics. Now, they're not undisputable, but we can look at, there are certain universal characteristics. So there's this debate in cultural evolution as to whether culture is universal. It's a very long-standing debate. People have made cases for it and against it. And in language, it's much the same, where you have people ask, well, language is very diverse, but are there universal things about language that can be extracted from any one language and applied to any other language? So, we can't say that language is strictly universal, but you do have these universal characteristics. So, this comes from very high levels of variation across the 7,000 or so languages that exist today that have been documented. There are other languages that exist. We have languages that are dead or dying. We have languages that are being created right now. And so these are not this is not a static process. This is just, a cultural tool that we have, but there's a lot of variation in languages. So, for example, linguistic differences between Japanese and English lead to a ratio of 1 to 11 in their number of distinct syllables. So, in Japanese and in English, there's a huge difference in the number of distinct syllables used. Now, you can encode similar meanings. You can use that language to do things, but the number of syllables, formal syllables, are different. So, you can think of it as representation. So if you're representing a problem, maybe computationally, we have the same problem, where if you use a data structure that's very sparse versus very rich, you can maybe represent more things, but in language that's typically not the constraint. We can represent things. And sometimes their concepts still get represented in languages, but there isn't any real, I don't think there's any real difference between languages in terms of what their capacity to represent things. It's just in maybe the things that are part of the culture or not part of the culture. So in Japanese, for example, there's umami, which is a certain type of taste, and that's not represented in English. We had to borrow the word from Japanese. So it's, they have, of course, concepts and words that we don't as English speakers. And so, so it's not so much that the number of syllables is a constraint. It's a constraint in the sense that you can't make those syllables, but you still work out, a reasonable amount of representational capacity there. These differences in repertoire size result in large variation in the amount of information they encode per syllable. So there's a lot of variation in how much can be encoded per syllable. So Japanese has fewer syllables, but they can still encode information. But then that rate of information encoding per syllable is larger. So there's going to be large variation. And so we can measure this using Shannon's theory of communication, or Shannon information. Let's see if they have anything good here in the results. This shows, so this is figure 1. They have these two measures, SR or IR. And so SR is syllables per second, and IR is bits per second. So syllables are in the language. They're sounds that you make, that you put together to make words. And then bits per second is the information rate. So SR is on the left here, and IR is on the right. And then we have this density by language. So on the y-axis, we have these different languages. I don't know, maybe you recognize some of the abbreviations. I think this is Thai, this is Vietnamese, this is maybe German, English, French, Korean. So they have all these languages, and they kind of average them together in this all category. So and then we have language family. So some languages are part of a certain language family. So for example, Korean and Japanese, well, they're in different language families actually, but you have Japanese here, Korean here, you have Austroasiatic, you have Basque, you have Indo-European. So a lot of the European languages are all Indo-European. So English and Italian are Indo-European. They're in the same family. Japanese and Korean are in different families. So, there's certain degrees of relatedness to these languages. And so we can see that, so for the SR, which is syllables per second, we see that Japanese is very high. I think Spanish here is also high. Finnish is, and then you get down to Vietnamese and Thai. Okay, so there's this variation in syllables. We can plot them out in order. And then this bits per second, we can see that, they're kind of similarly arranged, although not as much so. Whereas in Japanese, for example, you have a huge difference between Japanese and Thai in terms of syllables per second. That bit rate is limited in terms of the increase. So Japanese, communicates more bits than in Thai, or Vietnamese. Actually, Vietnamese, I think they're probably around the same. And so, you have this relationship between syllables and information. And then this graph here, which is figure 2, this is the relationship between SR and ID. And so this is across languages. So these are the language families, these circles, and they have the language families here. And then you have the labeled languages here. And then you have this trend. And I think, so colors represent the language families and individual languages identified by the labels on top. Short black lines. While there is only one value of ID per language, there are many values of SR per language as texts read by individual speakers. And so the yellow line represents the linear regression, and the black curve represents the locally estimated scatter plot. So they use a smoothing regression here, and then the yellow is the trend line. And so they're fitting all these data to these lines, so you have this, this measure of SR. As SR is decreasing, ID is increasing, basically. And so you can see that, sometimes when you have these kind of plots where you have a lot of variation per point, So you see the labels for the languages. These are the language families kind of splayed out here. When you have a lot of variation, it's kind of hard to do some curve fitting. So like this regression goes through these lines, but look at how much variation there is in each category. There's a tendency to go down, but that isn't always it's not always the case that, you know, that represents a significant difference, if you want to put it that way. You know, there's a lot of variation in each category, but there's this tendency to go downward. So it's, you know, I'm not a fan of this kind of an analysis, but that's what's true. Okay, so there's a lot of things, you know, if you're interested in linguistics, I think you can get a lot out of this paper. And even if you're not, I think it's interesting to look at to see, you know, what like cultural variation, the role that plays in this, you know, in the structure of language and in the information content of language. And it's especially interesting to think about it in terms of large language models, and especially when we're training large language models on different languages, and, you know, thinking about the performance and all that. So I think that's good for that paper. Any comments or questions on that?
I do wonder if there are, like, if there's something interesting about outliers, like if there are languages that are real, it's hard to say outlier because there was so much variability, but like really anomalous languages. It'd be interesting to explore maybe why some languages might not fit that pattern. Because that's a cool paper, but, and this is the case with, I don't know, maybe science in general, but it's probably masking a lot of really interesting details and nuances about different languages.
Yeah, so I mean, one of the things we assume about, or one of the models I use in terms of linguistic evolution, so like from language families to specific languages, is that you have this phylogenetic model where there's this divergence of languages. And, you know, sometimes languages are like, you know, maybe self-contained in that way, like they diverge and then they remain separate. And sometimes languages, you know, there are a lot of loan words. Like in English, we have a lot of loan words, in American English especially, a lot of loan words from other places. Yeah. And so, and so that's, you know, that kind of mucks up with, like if you try to characterize English, you say, okay, it's English, but then there's this loan word from some Native American language, or a loan word from Spanish, or a loan word from somewhere else. And those are going to violate the rules of English. So, you know, depending on the word, it's going to vary individually. And then within a language family, there are a lot of different languages there. So you have, you know, a large variety of languages that can exist. And you know, they evolve under different conditions. Sometimes language families span an entire continent or more. So that's a lot of variation, you know, in a lot of potential loan words and all that. So that's a good point, is that it's not, no, there is, like I said, there is a lot of variation there, but you have to, I guess, start somewhere. But I'll talk about this paper here, which is a dynamical systems view of neuroethology. And we've talked about naturalistic behaviors before, and we've talked about other kinds of, we've kind of talked about ethology in terms of animal behavior. Now we've talked about there's some ideas here that intersect with like behaviorism and some with cognition, but it's really, this is about like, you know, neuroethology, which is animal behavior, but it's about the neural substrates of animal behavior. So like ethology really was built around this idea of observing animal behaviors by looking at what they're doing, their external states. And so neuroethology is really about looking at those external behaviors, but then looking at what's going on in the brain. So this is an area that's been, you know, it has had a literature around it for quite some time. And so this is where they talk about a dynamical systems view. So we've talked about dynamical cognition and some of the ways people have approached that in our cognition futures group, but this is like a little bit different sort of goal here, is to get dynamical systems view of neuroethology. And so what they're interested in this paper especially is uncovering stateful computation in natural behaviors. So that means that you have, usually a lot of experiments or like in computational cognitive science or something like that, they'll do these trial-based experiments where they, you'll repeat something and they'll get a good signal for that event, and then they'll build a computational model of the brain saying this is, memory or this is learning or whatever. And so then it said, well, that's what's going on in the brain over this trial. But of course, we don't behave trial by trial. We behave in natural settings. So we might sit here in the meeting and kind of pay attention and sometimes not, and kind of just sit there and, maybe take notes. And that's all naturalistic behavior. That's not it's not entirely intentional, but it's also not entirely devoid of our cognitive processes. So let's go to the abstract here. State-dependent computation is key to cognition in both biological and artificial systems. Alan Turing recognized the power of stateful computation when he created the Turing machine with theoretically infinite computational capacity in 1936. So this statement here is, of course, an assumption that, behavior is somehow capturable by computation, and especially stateful computation. So we've talked about, Turing tests and that sort of thing. Actually, in the cybernetics group, we had this link between, thinking computationally about biology and how biology is maybe inherently not computational. In this case, what they're interested in is the state-dependent computation where you have this process that's producing states, or that it's dependent on states. So this is an interesting starting point where you kind of assume that there's this role for computation in this endeavor. Independently, by 1950, ethologists such as Tinbergen and Lorenz, and Tinbergen, of course, introduced the four sort of rules for looking at animal behavior, and we've talked about those in the past. And then Lorenz is another animal behaviorist who had some interesting things to say about, basic, especially with respect to innate behaviors and things like that. Also began to implicitly embed rudimentary forms of state-dependent computation. So they actually, Tinbergen and Lorenz, and we're not in the computer science area at all. In fact, this was back around the time that cybernetics was very big. Also began to implicitly embed rudimentary forms of state-dependent computation to create qualitative models of internal drives. So internal drives, that's a concept from psychology in the early to mid-20th century, where even before that, where they talked about these internal states, and you had drives and things like that. So there's this, they tried to take that idea and create models of it for animal behavior and sort of explain behaviors in that way. So you're not looking at the brain, you're looking at sort of this internal model, which is a black box perhaps, or something that, a model that generates behaviors. And then you're looking at that in terms of, states that are emitted by that. So you have different states of behavior. They relate from different internal drives and so forth. Here, we reformulate core ethological concepts in explicitly dynamical systems terms for stateful computation. So as you can imagine, that version of the internal drive, or looking at things in terms of internal drives, that's not really neuroethological. So you have to reformulate that whole enterprise to sort of come up with something that's compatible with neuroethology. We examined, based on a wealth of recent neural data collected during complex innate behaviors across species. So again, what they're doing here is they're looking at innate behaviors, which, if you look at different bird species and different lizard species, and there are a lot of innate behaviors that you can probe. And in fact, when you go and study an organism, you might create a catalog of behaviors that are, commonly observed. A lot of those being innate. You have, different types of behaviors that are sort of automatic. And so they have this, they have this set of behaviors. That's not really the problem. The problem is the neural substrate of that. And so the neural dynamics that determine the temporal structure of internal states. So from this data, they can extract these dynamics that determine the temporal structure of these states. So instead of just saying that they're drives or that there's something like non-specific that's related to this observable behavior, you now have neural dynamics that you can actually say, this is related to, this state that's going to be expressed. There's this temporal structure to it, and we can look at the neural dynamics. We can be specific there. We will also discuss the degree to which the brain can be hierarchically partitioned into nested dynamical systems. So we can actually look at, I wouldn't call it modularity, but the brain actually has these nested dynamical systems, meaning that there are different processes going on, different dynamical systems unfolding simultaneously, and that they're nested. So one dynamical system is related to another. And then, of course, there's also the need for a multidimensional state space model of the neuromodulatory system that underlies motivational and affective states. So this is where we have these dynamical systems, but then we also need a multidimensional state space model to represent these systems. And so this is the sort of where they're going with this. So they're going back to the history of ethology. They're looking at some of the practices of the past, which were just basically looking at animals, looking at their behaviors, kind of saying that their drives, a lot of them being innate and some of them being learned. And then, looking at these behaviors in terms of sort of internal drives. And then maybe asking questions about their evolution and their development, which is all a good enterprise. But you also now have neural data that we can link to that. We can say this is how the brain is generating these behaviors, and we can get a better sense of these internal states and their structure. So let's see. So this is where they talk about Turing's universal machine, or the Turing machine, for stateful computation. The Turing machine and the more limited finite state machine both rely on principles of state-dependent computation. So if you know what a finite state machine is, it's a series of states that are linked by transitions. And so we can say that this finite state machine represents all the states. We can construct a finite state machine to say these are all the states in the system. And those states have transitions between them, so we don't stay in one state forever. Sometimes we make transitions between states, or the state gets renewed, and we can model it using a discrete model of computation. So this is something that's very useful, I think, as an abstraction. We're looking at state-dependent computation. Whether this actually exists internally to the organism is another matter entirely. But this is the kind of model that you can really kind of use to make progress on some of these things. So state-dependent computation is defined as input together with the current system state, not only generates state-dependent output, but also determines the system state at the next time step. So this is the model that we're using, this dynamical model. It's based on the finite state machine. So by 1950, and we're going back in history now, by 1950, ethologists had also begun to formalize rudimentary forms of state-dependent computation to account for naturally occurring innate animal behavior. So this is these citations here. So in 1951, Carl Lashley most clearly and forcefully articulated the idea that state-dependent computation in the organization of movement sequences in natural language. So this is the idea that you can take things like movement in natural language and model them with this kind of state-dependent computation. Input is never in a quiescent or static system. So the input is never into a system that just kind of reflects the input as an output, or it doesn't just take in input and do nothing with it. There's always this, this sort of, the brain is doing a lot of things, and when input gets put into the brain or inputted into the brain, it's this, wild ride, basically. So input is never into a quiescent or static system, but always into a system which is already actively excited and organized. So the input, when you think about an input into the brain, it's not just into a box that it starts to, they're not like independent things. You don't have an input, it plugs into a system, it starts to process, and then it puts it out. It's kind of like, putting a piece of wood into a wood chipper. You put it in, it does something to the wood, it transforms it, and then it goes out. And then you put another piece of wood in. I mean, that's a serial model of wood chipping. But, in this case, what we have is the system that has inputs put into it. Those inputs might get stored, retained. They might get passed into outputs immediately. They might get retained for later. And there's a lot of noise and dynamical churn going on in the model. So your input is going into a model that has a lot of stuff going on. And so, it's not enough just to say that an input is this, has this size effect, and have it be this sort of deterministic thing. So that was Carl Ashley. In the intact organism, behavior is the result of interactions between this background of excitation with input of any designated stimulus. So that's from Carl Ashley, citation 4. At the same time as this statement was made, and this was, of course, in neuroscience more generally, in order to create a model of hierarchically organized behaviors, Nico Tinbergen also, in effect, borrowed two key concepts of state-dependent computation. So the first one for Tinbergen was this set of input-output relationships, and that those are dependent on the internal brain size, or the internal brain state. So the input-output relationships, if you put in an input into this black box, you get an output. This is dependent on the internal brain state. So if the brain is primed for the inputs, it does things with the inputs, maybe in a more sensitive way than it would otherwise. And it produces an appropriate output to that sensitivity. So you might have, you might take inputs, bring them into the brain. The brain is, sort of already maybe learned some of these things. And so the output is going to be much more organized than if the input goes into a brain that isn't trained on what the input is. And so this is, I think, a good recognition of that it isn't just that the internal brain state isn't just a black box, that you can't define it as like this, just as means of processing input, but the inputs are contributing to something that's already going on, a process that's already going on, and it gives an output appropriately. So only when a predator has the urge to hunt does the sight of prey induce an attack. Okay, that's the idea here. So if the predator sees prey and it doesn't have the urge to hunt, then it won't attack prey. If the predator is full, then the prey is okay, safe. But if the predator has the urge to hunt, then the prey is not okay. So it's a conditional statement. The predator will hunt if hungry or if urged to do so. Or if there's also has to be prey present. But, that's the idea. Second, state transitions depend on both input and the current state. So state transitions depend on input and the current state. So this is where we have our finite state machine. And we have our states modeled as these discrete units. And that's fine, but something has to drive the transition from one state to another, or, the system remaining in the same state. And so we have input, but it's dependent on the current state. So, we have these states that we can transition to, given an input, but the input is also constrained by the current state. So, again, with this example of the predator, if there's no urge to hunt, the state is in a sort of maybe a quiescent state. And if there's an input signal of a prey in the area, then that doesn't really trigger a change of state. It just stays in the same state. So in Tinbergen's model, the urge to reproduce is a brain state that conditionally permits transition to a limited set of possible future brain states that generate distinct behavioral patterns. So like courting or fighting. So the idea is that, you have this, in Tinbergen's model, you have this urge to reproduce, and there's this, there are things that need to be involved with that. So reproduction, of course, courting and fighting are related to reproduction, but not in all species. It just depends on the species. It depends on, these, it depends, first of all, on the imperative to reproduce, but also on sort of the things that are related to that. So, you might have, say, for example, a finite state machine where you have reproduction and you have some courting behavior or fighting behavior that might lead to reproduction or be a consequence of reproduction. And that can change in different species depending on their behaviors. So you can draw out those states and the dependencies between states in that way. Which state transition occurs depends on the interaction between the current state and the external input. So again, the input and the current state combine to determine these state transitions. Though Tinbergen was perhaps not explicitly thinking in dynamical systems terms, embedded in his qualitative model of hierarchical behavior are the two conceptual ideas that combine to form a dynamical systems view of internal brain states and animal behavior. So box 1 shows this well. This is innate behavioral hierarchies across species. So what Tinbergen was trying to build was a hierarchy. So, this is where we have this finite state machine. We have these circles, which are states. We have transitions between the states. So we have like these different levels. So the first level here is level of the major instinct, which is reproductive, for example. And the second level is fighting or nesting. So these are reproductive associated behaviors. And of course, the imperative to reproduce influences the expression of these behaviors. So if like a lot of animals are seasonal, they reproduce seasonally. If they're not in a reproductive state, they don't do these things. You don't expect to find fighting or nesting in reproductively inactive time periods. Then the third level is consumatory act. The fourth level is fins. The fifth level is fin rays. The sixth level is muscles. Seventh level is motor units. So what he's doing here is building this sort of vertically organized model of different phenotypic characteristics which are related to reproduction. So you might have muscles, motor units, which are parts of muscles that make them, contract in different ways. Fin rays, fins, those are important for reproduction as well, indirectly. And then this is all linked to this consumatory act. And so you see what you're doing here is you have these coordinate relations and these inhibitive interactions. So the coordinative interrelations are things in the physiology that kind of combine to enable behaviors. And then the inhibitive interactions are the things that need to be there in order to drive the larger thing. So if you have reproductive, the reproductive instinct, if that's present, then you get all these different things going on. If not, it doesn't happen. And of course, you don't have these coordinative interrelations in states that aren't occurring, but you do have them in states that are occurring. So this is just an overview of Tinbergen's model and where he was thinking and where he was going with this. And what they're basically doing here is they're modeling this. They're modeling some behaviors as feedback loops. So this is I think this is a C. elegans, in fact, where they're modeling head casts or head bends. And so in C. elegans, which are a famous model, they have a lot of stereotypical behaviors, a lot of stereotypical movements that you can model using these type of box and arrow models or these finite state machines. So this is where we have the first example here is where we have a forward reverse cycle. So you can see that the head bends in different directions based on the movement of the worm. You have forward and reverse, and it happens at a certain frequency. from the forward state, you cycle between these states. And then in the forward state, you have these propagated bends, which is dorsal ventral, and this happens at a certain frequency, and there's a loop there. And then each state there, dorsal or ventral, which is the orientation of the bend. So you can see it's moving in this dorsal ventral direction. Dorsal and ventral are sort of renewed, so you have dorsal and ventral cycling, which happens at 0.5 hertz for propagated bends. Then for head casts, when they stick their head out, when they're not bending their body, but sticking their head out, they do this dorsally or ventrally at 1 hertz intervals, and that kind of renews the state. So that they stay in the dorsal state when they're doing head casts, or the ventral state. They have events that happen at about 1 hertz, which is, I guess, a cycle per second. And then you go up to dorsal ventral, which is this loop. You have these propagated bends where they're moving back and forth. They're transitioning between these two states at 0.5 hertz. And then the forward reverse cycle, which is even faster, 0.05 hertz, is where they move back and forth between forward and reverse. So there are all these nested behaviors, nested dynamical systems here. This is a dynamical system, this is a dynamical system, and this is a dynamical system. They all have their own rate at which they're operating. So that's where this kind of nested dynamical systems idea comes from. That you have in a forward cycle, you have a dorsal movement and a ventral movement, and those can be separated out. This is in the fruit fly. This is showing kind of the effect of things on different behaviors. So you have these different discrete behaviors: receptivity, shoving, and chasing. You have these things that are inhibited, and these things that are sort of they exhibit positive feedback. So receptivity leads to shoving, whereas receptivity can inhibit chasing. And so these are, I guess, these are biochemical influences on that behavior. And then finally, we can think in a state-like manner in terms of the different types of foraging behavior in zebrafish. So there are these two different states, the exploitation state and the exploration state. And so these are two different states of sort of foraging. One is more exploitative, one is more explorative. And so if you look at this model, it's basically the same set of discrete states. You have free behavior, pursuit, prey in mouth or miss, and success or rejection. So free behavior is where free behavior enables pursuit. So it has to be able to behave freely. It has to be able to pursue the prey. It has to have then once it pursues the prey, it either captures the prey or misses the prey. And then if it captures the prey and swallows, then it's successful. If it spits it out, it's a rejection. So there are all these different ways in which the zebrafish will go after prey, consume prey, and so forth. And so these are, they've kind of characterized this with states and then some of these transitions. So free behavior requires the convergence of the eyes. Then that leads to pursuit. Then pursuit requires J-turns, or this approach swim. So they have to swim in a certain state. Then there has to be another capture swim that enables prey in mouth. And this speaks to these coordinate interrelations down here. So in the zebrafish, they're coordinating their motor units, their muscles, and their fin rays and other things to do these sorts of behaviors that they need to do. With the eyes, there's a convergence of eye muscles, where they have to be in that state. And then there are these other transitions. So you can either be successful, or you can have things like you can abort your pursuit, and the eyes become deconverged, and you go back to free behavior. And so this is the kind of model, and the model is tuned differently for these different types of behaviors. So when you're in the exploitation state, these behaviors happen a certain way. In the exploration state, these behaviors are executed in another way. So this is kind of a standard dynamical systems model. This is where they talk about the state-dependent computation with a nested dynamical systems model. they use very, very general terms here. They kind of go to almost like a control theory approach. And so this is what the diagram looks like. So U is the input vector. So U is the behavioral input. And we saw with the Gibsonian Information paper that the input is usually the thing that's bringing in things from the environment. We have F1 and F2, so we have basically two sort of states here, or DS. And so these are two dynamical systems, I'm sorry. There's an upper level dynamical system and a lower level dynamical system. And so what's interesting about this is that you have an input to both of them independently. So there's an input to dynamical system 1 and an input to dynamical system 2. But then dynamical system 1 feeds back into dynamical system 2. So if you have dynamical system 1 goes through its entire thing, and then it goes into dynamical system 2, and that happens. And then that feeds back to the environment. So you can think that this is like maybe an internal processing model. And then this dynamical system 2 is being something like the muscles, moving, the effectors moving the organism through the environment. So you might have the eyes as an input, visual input to this internal system that processes visual input. You can say maybe like a motor response. And then the motor response is something that happens in the muscles, and the state of the muscles enables a movement, and then that feeds back to the world where there's some action made on the world. So that's maybe one way to think about this. And so then we have our F here is the state update function. So we have an input and we have a state that the input is sort of enabling. And of course, remember, we have the system here, so we have all these other things going on. This state update function, though, is influenced by feedback. So in this case, in dynamical system 1, there's feedback from after the integration of information. And in dynamical system 2, that feedback comes from dynamical system 1. Then we have x.2, x.1, and x.2. Those are state vectors. So the input goes into this state. There's a state vector which describes that state. And then there's x.1 is the untransformed version of that. And then there's this integration. So you're taking a derivative of x.1, which is x1. That x1 can serve as feedback to the state, or it can serve as g, which is the output function. So it can inform the output function directly or serve as a feedback to the state. And then the output function will output to the second dynamical system its function. It goes x.2, this integration, and then x2. And x2, of course, feeds back to the original state, where it goes to this g, which is the output function, and then it produces an output into the world, into the environment. So this is an interesting paper. I think that's all I'm going to talk about for that paper. But let's see what we have in the chat here. Okay, so Sarrah, who is still here, I wonder if the findings from the paper could somehow impact the way language translation using deep learning works. Or maybe the finding in rates being similar is the reason it works. So yeah, we did talk about sort of at the end the large language model aspect of that first paper. And yeah, I think it's very interesting. I guess language translation is a thing they're doing with large language models now. I'm not sure. I'm familiar with how they train it on a corpus from a certain language. Sometimes they'll use they're very highly specialized large language models for languages that have very few speakers. And we talked about this once with respect to languages that are not English. And how you have to train them separately, but I think a lot of the large language model work that everyone's impressed with has been in English, so that's an interesting point. But also, yeah, I don't know what the relationship between that and translation are, but that'd be an interesting thing to find out. Morgan has something to say. Oh, Sarrah.
Sorry, I mean the neuroethology was just near and dear to my heart. we basically did that with crabs.
Okay, yeah.
Yeah. So this was back when I was looking at sleep-like states in invertebrates.
Oh, okay.
and anyway, so we had, rudimentary, this was the 90s. I'm dating myself here. But yeah, this was the 90s. So it was rudimentary motion capture plus electrical, basically EEG on the crabs to try and capture some physio information as well. Yeah. but we were trying to do this and distinguish basically the state that the crab was in as it moved through particular states.
Oh, okay.
And one of those we wanted to say was actually a sleep-like state.
Yeah.
This is cool. Has this been useful in like C. elegans? I mean, in terms of this hierarchical organization?
Yeah, I think in C. elegans we know like kind of the connectome and what it basically does. So we have these circuits that are movement circuits, and people characterize those. It's like maybe about 7 or 8 neurons that are at the core of that have like enable forward and backward movement. Mm. And then of course you have things that modulate other neurons that modulate that. And so having this, the way that I showed with the hierarchical, behaviors where you have these different oscillations happening at different rates, that's actually quite useful in terms of the modulation part. So like a lot of behaviors are of a state, but that state is not like just this single thing. It's like a lot of things within that state. So you could break down that state into substates. Like you said, defining a state is the key, but like defining the state also implies that it's very simple and has a single mechanism. And that may or may not be the case, right? Like,
well, it was interesting. I was trying to find the paper, so it was interesting the other references that came up when I gave as many of the search terms as I did, and one of those was Friston's variational ecology.
Oh wow!
But I think looking at the abstract, it spoke to the like this is allowing this kind of multi-scale action, right? So inside of these units, DS1, DS2, you can have another system, right? Yeah. And I thought it was interesting that box 1, the reference is a Cell paper that it from 2014. A framework for studying emotions across species.
Oh wow!
So, yeah, Anyway, it's made me want to. Yes. Sarah's got some more comments on the transformers. Okay. But yeah. Anyway, it brings up a lot of other papers that look really interesting too. Yeah. And I'm not, as someone who had to read Tinbergen, I don't remember this like what are we contrasting this with, and what are they? Yeah, what are they adding, or is this just a review? I forget where this was. This was current opinion in neurobiology.
Yeah. So it's maybe a reviewish kind of thing.
Yeah, this is kind of reviewish, right? I mean, it's like
Yeah, I think maybe what they're adding. Well, they don't really like specifying the neural circuits. They're really kind of laying out this control kind of aspect to it. And then, that's generic for like any neural circuit that you want to put in. So, I mean, the Tinbergen stuff is purely qualitative in that sense. It's just like, here are the states, we're going to define them.
Yeah.
But
for sure. Well, it was also coming up with good. It was coming up with good input vectors, right? That change states. Right, so I mean, definitely the well, the exploration gets you also kind of into the current, agent learning literature too. And yeah, anyway, it's probably how you would, frame things these days in terms of your computational modeling of behavior. Right.
Yeah. I mean, then and again, there are a lot of connections to reinforcement learning, which we didn't talk about at all. Yeah. So this is like separate and apart from that, but it isn't, because you can use reinforcement learning as a tool to model those internal states, and and so this is definitely in the milieu at the time too, because that was when behaviorism was ascendant, and it had, there were influences there in terms of what shaped neuroethology. And so I thought you'd appreciate the Carl Lashley quote in the paper.
Sorry, a little multitasking. What was the quote?
Oh, let's see.
Was that in the abstract or the intro?
Yeah, I think so.
I think I saw something.
Yeah, this one here. Let me see. Am I sharing my screen still?
Yeah.
All right. So it's this one here. In 1951, Lashley most clearly and forcefully articulated the idea that state-dependent computation and the organization of movement sequences is natural language, and this is the quote here.
Definitely. Yeah. That sounds like something that Preprint would have liked if Lashley's too.
Yeah. The problem of serial order in behavior is the name of that reference.
Yeah. For sure. I would love to see what that Cell paper is about. I mean, I love. I forget who was pushing this. Couple of groups here in neurotech have been pushing, focus on sleep and dreaming, and it always reminds me of the. We don't exactly know why we do these things.
Yeah.
And that cross species analysis and research, it can be so useful for addressing that. For like, one thing I know for sure is that my dogs dream.
Yeah.
They sleep and they dream.
Yeah.
And they, we were also up at Tahoe, so my daughter was sleeping in our room, and saying something about like playing and eating, like in her sleep, so it's as far as we are with things in neuroscience, we still don't know why we actually sleep.
Yeah, maybe a lot of things too. Like
right. Yeah, well, it'd be interesting that classification of these states as emotions. Oh,
right.
Here, sir.
Yeah, so sorry. Thanks for attending. And I wanted to go over your comment. Language translation is mostly done with transformers using encoder-decoder architectures. The use of encodings is what made me curious about the aspect of translation. It works a lot based on the encodings or embeddings of sentences, both the languages being similar from an extremely condensed perspective. Yeah, there are a lot of... So encodings, of course, in large language models rely on the structure. And in linguistics, there's a lot of work on like the structure of language. So that's something, if you're interested in that, there's probably some literature in linguistics on structure. People don't talk about that as much when they, like, the technical aspect of large language models is sort of dependent on that, but it's not discussed a lot when we just talk about the capabilities of large language models. And so that would be interesting to kind of think about a little bit. I assume the different rates from the world matter, and maybe it could be used to understand how efficient translation would be. Yeah, I think definitely the information content of languages and looking at translation and that sort of thing, it's always good, kind of good to consider. And again, there's probably a lot there that can be worked on, like in terms of thinking about, what people know about language and how large language models perform. So definitely a good thing to think about there. Yeah, so thank you for that comment. And I don't know, Morgan, I thought you might have something to say about large language models. That's why
I do. I wanted to. Sorry, I still spring break here, but I wanted to look at that paper more closely. But there's a whole bunch of questions that it raises too, or ideas that it raises that would be really interesting. We need to return to this. I mean, as much as I agree that it's not the direction for AGI, they're still fascinating models.
Oh yeah,
that have so much. So endless avenues of inquiry there.
Yeah, definitely.
But I also wanted to at some point ask Sarah about her octave work.
What is that?
I know she needs to go. Well, I saw that she worked on GNU Octave.
Oh, okay, yeah.
I had worked on it on my previous GSOC in 2022.
Yeah.
So I had worked with Professor Carlo De Falco, and basically my work was in the ODE 15IS solvers. I mean, I was not working on it from the mathematical point of view.
Sure.
I was working in the computation where the solver was already implemented and they were using an algorithm.
Yeah.
And they were using the algorithm from another library, which was not that efficient. So basically my work was to kind of try to make as many wrapper functions as possible and use as many GNU Octave is all of its operations are vectorized, which make them very fast and efficient. So the idea was to try to use those operators while still utilizing the KLU algorithm for the solver from another library.
I see.
So that is what the project was.
That's awesome. I mean, it's such an important, that's one of those, especially in computational world, it's one of those open source projects that is so important, but it doesn't get the, not everybody knows about it. And
yes.
but it's super valuable tool. And so people in neuroimaging are involved in GNU Octave because of SPM Toolbox is a MATLAB package. So they actually use SPM as a use case for GNU Octave. Because SPM is such an old MATLAB toolbox, they feel like if they can get SPM to run, that they have Octave done, but it has a lot more, I think, to do with the GUI tools as well, or GUI functions than back end computational work like you were doing. But it's very cool, very cool. I know you got to go, so I just
right, sure.
I love that. Yeah.
Yes.
And we should talk more language models. Yeah.
Yes, definitely. Goodbye.
Thank you.
Yeah, computational linguistics, another whole area to cover.
Yeah, definitely.
Yeah, some interesting. It was some opinion piece on the Chomsky's rule of computational linguistics and what that's given over the 50 years.
Oh yeah,
50 years plus that he's been in. Anyway,
I think that's actually something that Harry Marcus is a linguist by training. So he's very interested in this, and it's like the rubber's hitting the road in terms of testing a lot of the things that they've been talking about for years.
For sure.
I mean, they've been able to do experimentally, but this is giving them a whole new avenue.
Yeah. And I forget the LingBuzz is the archive for linguistics. Yeah. is still interesting to see, because these large language models have brought a lot of new voices into what is definitely is computational linguistics, like whether you want to say it's whether it's Chomskyan linguistics.
This is a paper that came out. This is Andy Clark, Friston, and Constant. So Friston and Constant, of course, are active inference people. Andy Clark is, of course, general philosophy of mind. So this is interesting that they're kind of producing this publications. This is from Philosophical Transactions of the Royal Society B. And this is called Cultivating Creativity, Predictive Brains, and the Enlightened Room Problem. So again, this is a collaboration between like our active inference people and Andy Clark, and so who's also an advocate of active inference, but that's not what he's best known for, I guess. So the abstract here reads, how can one conciliate the claim that humans are uncertainty minimizing systems that seek to navigate predictable and familiar environments with the claim that humans can be creative? So this is, this speaks to sort of this idea of the free energy principle, but also this idea that, there's this minimization in cognition, that, there's this optimality, that you're basically trying to learn, say like an environment or what's in the environment, and, doing that optimally. And then, of course, creativity being sort of the flip side of that. So, you have the free energy principle, which suggests that there are these sort of variational paths to success, and then those are selected from. But then creativity that kind of flies in the face of that. And so, and it's not just, active inference that argues this. It's, basically the whole enterprise of cognitive science, because cognitive science is about sort of, problem solving and optimization, and sort of minimizing error. And so this is, a problem. And then, of course, creativity, of course, is where you have things that you wouldn't expect and putting ideas together that don't exist. And so people have, as an aside, there also is this literature in evolutionary computation on creativity as well. So people have been working on this problem from multiple perspectives. There's also a lot of work in cognitive science on creativity, and I'm not sure what they're citing in this paper, so I guess we'll find out. So this sort of contrast between this minimizing system and this creative system is called the enlightened room problem, or ERP. And it's not the brain signal, it's the enlightened room problem. The solution we suggest lies not only in the error minimizing brain, but in the environment itself. So they're still sticking by sort of the free energy principle aspect of error minimization, but also that the environment plays a role in this. So creativity emerges from various degrees of interplay between predictive brains and changing environments. So there's this idea, of course, of predictive processing, where there's this idea that there's this feedback loop that enhances prediction, and that the brain is a predictive machine. So when they say predictive brains, they mean the brain is basically trying to predict things, and as a consequence of being a prediction machine, it minimizes its error so it can make those predictions successfully. So there's an interplay between the predictive brain model and changing environments. So the predictive brain would be excellent if the environment were static. So if you just trained your brain on a static environment, you could learn everything pretty quickly. You'd have this feedback loop that tells you, there's a signal that tells you that, there's a prediction for the next step, and you can navigate through these static environments pretty easily, and the world would be a pretty boring place. But what they're arguing is that the environment's always changing, so that predictive brains do their thing, but they're always challenged by the changing environment. So the prediction is always, we always have to change that feedback loop in terms of its contents in order to really minimize the error in that changing environment with respect to that changing environment. And so the way they put it is ones that repeatedly move the goalposts for our own error minimizing machinery. So the goalposts are moved for that error minimization. You introduce more error with the changing environment and you keep minimizing it. So it's a kind of an interesting way of viewing this. Obviously, we have to deal with the changing environment because we have this naturalistic view of things. And if we do this in an experimental setting, again, like I said, in terms of the neuroethology paper, those experiments as trial-by-trial experiments are generally kind of a static environment. You give like a very specific set of instructions, a very specific task, and that task isn't supposed to change. That's the whole point of the experiment. But this sort of naturalistic view, you're interacting with a changing environment. You're always exploring new aspects of the environment. So by co-constructing these challenging worlds, we effectively alter and expand the space within which our own prediction engines operate, and that function is exploration bubbles that enable information seeking, uncertainty minimizing minds to penetrate deeper and deeper into the artistic, scientific, and engineering space. So they talk about these exploration bubbles, which I guess they're going to define later. But this is, of course, extending that prediction engine, extending that predictive space through experience. And so this is where they're exploring, new areas that haven't been encountered before. In what follows, we offer a proof of principle for this kind of environmentally led cognitive expansion. So it's again an expansion of cognition, like maybe new labels of things, or new spaces, or new relationships or relations. And so those have to be learned. So this is an area in machine learning too that is a problem. And we talked about this a little bit on Thursday with respect to why the authors of that paper don't like the idea of computation or of cognition as computation, and that is because you have things that haven't been seen before. You have to expand the model somehow. So you train a model on certain things, and then they always encounter new things. It's not just the interactions between existing knowledge that they're trained on, so it's not just the interactions in the internal model, but it's interactions with things in the world that are presented, and how those are presented in time or in space and those sorts of things. And to do that, your conceptual model has to be expanded out quite a bit. So, if you encounter a new food or encounter a new concept or a new taste, those things have to be put into a framework. And if they're put into the old framework, they can be misattributed, or, you can have prediction errors. So that's kind of an interesting point to put aside for at least the machine learning aspect, but also some of the stuff about the brain as a computer or algorithmic approaches. And then, this article is part of this theme, art, aesthetics, and predictive processing. So there's the special issue that Royal Society put out on this. It was actually a couple months ago, I think, February. So, Andy Clark is a big predictive processing advocate. So predictive processing seeks to explain animal behavior and cognitive functions, as well as their underlying neurophysiology in terms of Bayesian inference processes. So we have these feedback loops that are usually operate, we usually try to put some sort of, neural imprimatur on them, it could be dopamine signaling, it could be, some other type of set of connections that are producing this feedback loop. Well, we model it in terms of Bayesian inference. So we say, there's this prior, that the prior sort of sets up the predictions for the future, and then you observe the world and you kind of match the prior with the observation, and you get a posterior, and that posterior then updates the prior. Oh, you wanted to say something, Morgan?
Oh, sorry, I was clearing my throat.
Oh, okay.
No, I mean, really interesting, and of course, this again makes me think about Ken Stanley's work.
Oh, yeah.
Especially his early work in terms of trying to get, even just some of his image. What was that image generation tool he created? Anyway, it allowed for evolutionary generation of images.
I think it was Pick Breeder, maybe, or something like that.
Yes. But like, again, it's getting at this. So one was just like people using it to see what interesting images would come along, right?
Yeah.
And it being hard to, this is before diffusion models, things like that. So it was hard to drive it, or to prompt it.
Yeah.
and so people would just let run, and they would just be viewing, like, using themselves as a pattern detector to be like, oh, that's an interesting.
Oh yeah.
And then trying to see how, compositionally, like things had been broken down and then composed in new and interesting ways, right?
Yeah.
So anyway, you see in this also a lot of the debates in evolutionary theory too, right? In terms of how speciation is exploring and exploiting niches, but also, like how you come up with a novel, a novel case, or creativity being a very hard word to describe.
Yeah.
But definitely a big difference in terms of looking at things open-ended. Again, like this is just at the time it was really new in terms of Ken Stanley and kind of other A-life gecko people.
Right.
Changing the context for how we were discussing these things, right?
Yeah.
And
Well, yeah, there's this definite strain of open-endedness in this. They don't call it that, but that's what it is.
Yes, for sure, right? And again, just because it's Andy Clark, just thinking about Carmel F. Smith's work. That so he worked with Carmel F. Smith, and that he's fully aware of her work in terms of trying to get kids, looking at kids' drawings and seeing what they were capable of generating that they hadn't seen before, right? And that was a super interesting neo-Piagetian task.
Yeah.
Because it was really revealing. I mean, she wanted to say that you could find these age ranges where kids weren't able to step out of their kind of just they had no creativity. Right. So there was no way they could draw something that they hadn't seen or weren't able to. They didn't have a motor program for. And then there would be this kind of new period where they were able to perhaps generate something new. Anyway, really interesting topic, and I think Amanda would love this. Yeah.
So let's see. And then they get into kind of predictive processing. They use this kind of approach. So they're, predictive processing, of course, is this feedback loop that's implemented using sort of a Bayesian model of inference. And the point here is that PP can be read as the umbrella term for many theories of the predictive brain. So when people say predictive brain, they're usually referring to like a Bayesian process and then this predictive processing more generally. And that stands out from like the evolutionary approaches that we're just talking about. In that, in an evolutionary approach, you have this generative model that is driven by selection. So the idea would be you would prompt a model, or you would put in some like if you're evolving art, you might put in some primitive shapes, and then you run the model and they put it together in different ways, and then you select the outcomes that maybe look interesting, and then you do another round of simulation, and that produces new outcomes in that subspace, and then so you do these rounds of selection and generation, and you end up with this thing that maybe you never would have come up with on your own. That was one of the original rationales for genetic programming or genetic computing, is that you can use this biologically driven process to produce creative solutions, things that explore that possibility space in a way that the human mind might not, or it generates a lot of outcomes that are interesting. With predictive processing, though, we're kind of at the other end of it. We're kind of saying we're selecting on action kind of optimally. So we're taking all those outcomes and we're kind of saying this is the optimal thing. And then what they're saying is, well, you need to inject some sort of to get creativity, you need to inject maybe some noise into this predictive processing model. So if you think about the predictive processing model as sort of that selection of things coming out of the generative model, you run the generative model again, and you get new outcomes that then you have to select for, and so forth. So predictive processing is maybe predicting maybe the best solution, but also having that generative process that's sort of breaking up the feedback loop, the way the feedback loop functions. So in a Bayesian model, you might have like a prior, and the prior might be, might be normally distributed. You might end up with a series of solutions from that prior. Then you might look at the environment and say, okay, these two things match. And then you might have your posterior, which is based on that, but also maybe some random noise that then sort of disrupts that cycle. So you have to make, that prior is no longer just kind of like refined. It has new things in it that you can then select from. So this is, kind of an interesting way. So they're basically drawing from predictive processing here. In predictive processing, action, perception, attention, and learning are all cast as inference processes over prior beliefs. So you have these prior beliefs in your internal model, things going on in the brain with respect to the inputs. You have these prior beliefs. So in the paper that we talked about, in the neuroethology paper, you might have a lot of, this might be something like drives or urges or, innate behaviors. In this case, it's prior beliefs. And so your input is going to impact those prior beliefs. They're going to influence them in some way. The inputs just don't go into a black box. They're actually prior beliefs or corollaries in there that you already have. Then these beliefs mapping the relation between the unknown or unobservable or latent variables, such as states of the world across time, and the observable outcomes that they are thought to cause. So this is the thing that we're trying to do in predictive processing, is map the relation between unobservable or latent variables like states of the world across time. So we don't know the state of the world just by looking at it once. We need to sort of infer the state of the world from many, many observations, and then kind of you link that to some observable outcome. So, for example, if the sun rises in the morning, and you look at other things in the world, you kind of look for a cause, or you look at what the sun rising causes. And sometimes that can lead to things that are not correct. There are a lot of, there's like what you might call folk physics, where we kind of make shortcuts across what we actually know as physics, and we make these sort of weird associations. But that's part of this process, is that because it's optimizing processing, that's sort of the consequence of that. And so this is all has a lot of there are a lot of maybe critiques of predictive processing or other things that predictive processing is. It's not. I wouldn't call it like a really predictive theory. People have made a lot of complaints about predictive processing in terms of like its effectiveness and also its sort of the way it kind of views the brain.
Yeah, I thought it was really interesting. I'm trying to remember I think it was Ryan Smith's recent active inference presentation talk that I thought it was really nice. For me, it was really informative about how active inference could, be put in the context of reinforcement learning, like agent training.
Yeah.
and like computationally where it fits in, like it's actually it's like the trade-offs that you're making between exploration and exploitation, and the functions that you're using for it, and and certainly his other point was that like active inference doesn't mean one thing anymore. It's now a set of things, and it is. I mean, it was his student's paper, but right. He was doing most of the talking, and and that computationally you could break how you could see each of these as like just a change of this, a change of that, in terms of these trade-offs or the function that you're using, or et cetera. But that's all in the context of agent training, right?
Right.
Like creativity, or like much more difficult to. Well, again, I haven't seen a computational definition of creativity.
Oh yeah, and it's going to be like intelligence, right? It's going to have a lot of different definitions.
But I did think it was interesting. Again, just trying to find the paper that you're reading.
Yeah.
That if you put in Clark and Friston, the references that you get in PubMed, or I think I just even had Clark in PubMed, and so one that the darkroom paper goes back with Friston like 10 plus years, like 2012, and so they've been banging on this for a while. But I also like the representation wars enacting an armistice through active inference. That's a great. A lot of creativity in these titles.
Oh, there we go. Yeah, breaks up predictive processing and
Yeah. I mean, it's a great list. And it would be really interesting to dig into this.
Yeah.
This was the 2024 Royal Society, right?
Yeah, this is the
Cultivating.
Yeah.
So he's got another one that's also this year with Clark, with Sisek, and Parr and Pazzullo, which are the textbook authors, if I'm correct.
Yes.
Yeah, so that sounds super interesting too. But generating meaning, active inference, and the scope and limits of passive AI.
Okay, wow.
But I said I would do this, and so I haven't yet. But I thought that Clark's Royal Institution talk that was like a week or two ago, he had some good references that I just needed to go through and find the right time and get from the slides. yeah, definitely would relate to predictive processing and stuff.
Yeah. So let's finish up this piece here. Yeah, we're getting towards the end. So some have argued that there is a fundamental limit to how much cognition and behavior one can explain with the constructs and predictions and prior beliefs under predictive processing. So this is where the darkroom problem comes into play. This suggests that if behavior was driven only by the imperative to minimize uncertainty, organisms like us would always be found in situations that are minimally uncertain and that preclude violations in our predictions. So this is what I was talking about with only just being the perfect predictor, but stumbling on things that you've not seen before. This problem has bred a large and varied literature, 10 through 16, which we just talked about. It is now clear that the DRP ignores the basic fact that prediction errors need to be minimized, both with respect to internal and external sensory evidence, allowing bodily requirements to exert a strong influence on behavior. So I don't know what that means. That they've explored this. The DRP, or the darkroom problem, ignores this. Prediction errors need to be minimized in both with respect to internal and external sensory evidence. So I guess it means that there's this internal model and what's going on in the external environment. And then bodily requirements, I guess maybe there's an embodiment aspect. That's 10, 12, and 15.
Well, I think that certainly to your point that you see this a lot in agent training, right?
Yeah.
Where the world generation, right, is really key to the agent's generalizability, right? So that like the more varied a world you can construct for the agent to learn in, then the better the agent.
Yeah.
Is it something like that? Or,
yeah, I guess. I guess what they're saying here, that they're talking about the darkroom problem, and then that it doesn't just involve predictive processing, and then they say it is now clear that, and this is after this literature has been written, it is now clear that the DRP ignores the basic fact that prediction errors need to be minimized, and then there are these conditions under which the prediction errors need to be minimized. So I guess what they're getting at is there is this trade-off between learning new things, you have to generalize the training, the actual behavior needs to generalize. You can't just have it we talked about the ability to generalize. And then, of course, this aspect of, optimization, but also of creativity, exploring new things. And it's not, I guess it's just kind of like this catch-22 that is still out there because they've been publishing on it for a long time.
Yeah. That, well, I like the last sentence there is definitely getting at the kind of world model problem.
Okay.
Right? It's across long-term time horizons too.
Yeah.
Right. So too much of the, I'm sure I always think, when I think of predictive processing, I think of, vision and auditory and, very simple cases.
Yeah.
And not thinking of, essentially these kind of world model, it's like I dropped in I think Dev AI. I think it was Andrew Ning, something like tool use, right? Is one of these ways in which agent behavior is really complexifying, and that's probably because it requires all this you've got to do this before that, and successive hierarchical decompositions, but also thinking way ahead.
Yeah.
In terms of I want to be able to do this, and therefore I've got to do X, Y, and Z.
Yeah, and compositionality, of course, being a very key aspect of artificial intelligence. But let's look at this last sentence here. Furthermore, many creatures minimize error across long-term time horizons. So it's not just about those local feedback loops, like minimizing on each observation of the environment and the prior. It's actually minimizing error across these long stretches of where you're doing these evaluations of what you're observing, the prior being updated, and so forth. But then also, if you have these local things, like if you observe some local variation and you optimize according to the local variation, then you might start to observe more. Like if you're maybe in a room and you're looking at the room and you learn what's in the room, and then you move to the rest of the house and there are different rooms with different things in them, you could optimize your behavior for that one room and then go out into the other rooms and not really understand what's going on because you've optimized yourself locally. So like moving across like a larger context or a longer term time horizon then is, and of course they say minimizing error as if like that's a process where we have access to that entire thing. We don't. We have variation within that global context, and sometimes we can observe parts of it and then optimize our behavior. And then I guess the thing here is what they're saying is, well, you optimize your behavior just enough, and then you move on to another one, and you do this over the long term. It all works out, which is maybe the problem here is that you're still saying, okay, there's optimization, and then there's this creativity, or there's this introduction of new things. And so what is the right amount of minimizing error? Well, it's just the right amount, and it works. Well, I don't know. I mean, that's maybe not the great way to think about it. And so then, but we can also think about this in ways that seek informative prediction errors. So these are prediction errors that are informative versus prediction errors that are just simply noise. So, when your prediction is made, you have a certain amount of error you're trying to minimize. But perhaps that some of this prediction error is informative. Like if I know, for example, if I'm throwing a ball at a target and I know that there's a systematic offset, there's a set of experiments where, there's the prism adaptation experiment, but there's also this one experiment that was done once where they put someone on a merry-go-round, or they put them on one of those, I don't know I can't remember what they call them. They're like these things that go around and you ride them and you.
I know what you're talking about.
Yeah, merry-go-round kind of thing.
Sort of. Yeah.
And they had this person ride this thing around in a rotational way, and then they had them throw clay balls at a target as they're moving. So the idea being that you know how to throw clay balls at a target, but if you're doing it rotationally, you haven't learned that yet, so you're making the systematic error.
Yeah.
And there's an inertial error that happens. And so, the idea is you're always making an error, but you know why, and you know how to offset that perhaps. So that's what it comes to mind when I think about informative error. That kind of why it's happening, or that it's error, but it does tell you about the environment somewhat. So but we don't, again, that's another problem where you have to have specific cases, or maybe we don't, we know kind of the global state, the way things should be. So it's not always the case. And so this is maybe the problem here, is that you have this assumption of we can just minimize enough, and we can get there. But
yeah. Sorry, I saw something, and I think it was from the ACX Astral Code.
Oh yeah.
I forget that. Yeah. Anyway, they was talking about how we're all say we're Bayesians,
yeah.
Right? But we can't actually do these computations, right? It's certainly not for real world problems.
Yeah.
We don't have all this stuff. So what are we actually doing, right? And I think, yeah. Anyway, to your point that we probably aren't doing the same kind of error minimization
right.
all the time, right? It might be error minimization, but I bet we're taking shortcuts. I bet we're making, we've got all these biases that we're using that are kind of hard coded, et cetera. Like, there is this. Anyway, I think we see it in that variational ecology. There's this certain desire to have the one theory that explains it all.
Yeah.
But it's probably good humility to remember it's probably not in our lifetime that we will have that theory.
Yeah.
We shouldn't try and push it. Anyway.
Yeah. So yeah, I mean, the heuristics cut both ways. Heuristics can help you get to that minimization, but it can also, like in the case of folk physics, it can mislead you because you have this model that's oversimplified. And
or I mean, the coming from Smith Kettlewell, it's just like optical illusions are a reminder and a tool.
Yeah, exactly.
Yeah. Anyway, I just I know I gotta go. I just wanted to say I dropped into DevAI this new paper with Daniel Friedman, Friston, and shared protensions in multi-agent active inference.
Yes.
I don't know if you'd seen that.
Yeah, I heard about it. We had a meeting this week for the Scientific Advisory Board, and they talked about this paper. So I'm glad you brought it up. This looks good.
It's got so many great institutions there.
Yeah.
Because I just dropped something in math about from the Topos Institute, and of course Versus is this new. I didn't realize they were calling it Research Lab and Foundation.
Huh.
That's interesting. Anyway, so and it's in LA.
Yeah.
Okay. But looking, it seems like it would be great to talk in terms of cognition futures.
Yeah.
They're referencing a lot of philosophy and other theories that we would.
We're familiar with from that.
Nice to look at.
Yeah, category theory and all that. Yeah.
Mm-hmm.
No, it's great. Yeah, it's great. All right. Well, thank you. I think that was a very good meeting. Again, we'll be this week is the GSOC deadline, the 2nd, and make sure you get your proposals in. And
that's Tuesday.
Yeah, Tuesday.
Okay.
And and we'll try to have as many meetings as possible this week. I don't know, but I think we're having a DVOR meeting this week as well as maybe the cognition futures. So that'd be good. Okay. All right.
Good.
Take care. Bye.
Take care. Bye.